What if I told you there's a kind of secret language that dictates everything from the power in an engine to the calories in your food? Well, today we're going to decode that language. We're talking about enthalpy.
So, let me ask you a question. How in the world do you measure the energy of a chemical reaction that's, well, impossible to actually run? Maybe it takes a million years, or maybe it's just way too dangerous. It sounds like a total dead end, right? But it turns out chemists have this brilliant workaround. And by the end of this, you're going to understand exactly how it works.
Okay, to solve this puzzle, we have to start with the basics. We need to understand how scientists keep track of energy. And you can really think of it like a universal accounting system, where every last bit of energy has to be accounted for.
You see, every single substance, from a drop of water to a chunk of metal, is basically a little reservoir of energy. All the jiggling, vibrating, and zipping around of its atoms and molecules, that total energy packed inside is called its internal energy. And we just use the letter U to represent it.
Now, this internal energy isn't just locked away. It can change. But, and this is the important part, it can only change in two ways. Energy can move around as heat, which we call Q. Think about a pan warming up on a stove. Or it can be transferred as work, W, like the work done by expanding gas pushing a piston. Heat and work, that's it. And this simple idea brings us to one of the cornerstones of all physics, the first law of thermodynamics. It is the universe's ultimate, unbreakable rulebook for energy. All it says is that the change in that internal energy, that's the delta U part, is exactly equal to the heat you add to the system plus the work done on the system. Bottom line, you can't just create or destroy energy out of thin air. You can only move it around.
So you might be thinking, great, to find the energy change, all we have to do is measure the heat and the work, right? Well, yeah, in theory, but in practice, it's not that simple. And that's why chemists came up with this incredibly clever shortcut.
So here's the real-world problem. Measuring heat flow, we're pretty good at that. But trying to also measure the work done, especially when you have gases expanding or contracting and pushing things around, that can get super complicated and messy in a real lab. So to get around this, scientists invented a new property. They called it enthalpy, and we used the letter H. Now, at first glance, the formula looks like we just made things more complicated. It's the internal energy plus the system's pressure times its volume. But trust me, hiding inside this new term is an amazing simplification.
And here it is, the big aha moment. It turns out that for any process that happens at a constant pressure, and let's be real, that's most chemical reactions happening in a beaker open to the air, the change in enthalpy, delta H, is exactly the same as the heat flow. All that complicated work stuff we were worried about, it just disappears from the equation.
And that is why enthalpy is such a total game changer. All of a sudden, chemists could just forget about that tricky pressure-volume work. If they wanted to know the energy change for a reaction, all they had to do was measure the heat. It's just an incredibly powerful and elegant shortcut.
Okay, so now we have this amazing tool, delta H. But like any tool, you got to know the rules to use it right. And luckily, they're pretty straightforward. The rules are super simple. If delta H is negative, it means the reaction gives off heat. It's exothermic, like a fire. If it's positive, it absorbs heat. It's endothermic, like an instant ice pack. Makes sense, right? If you run a reaction backwards, you just flip the sign of its delta H. And since enthalpy is all about the amount of stuff, if you use twice as much chemical, you get twice the delta H. And finally, you have to pay attention to whether something is a solid, liquid, or gas, because each state holds a different amount of energy.
All right, we've got all the pieces on the board now. We understand internal energy, heat, work, and enthalpy. So let's bring in the master key that's going to let us finally solve that impossible reaction problem. This key is called Hess's law.
The whole reason Hess's law works is because enthalpy is what we call a state function, and that's just a fancy way of saying it's a property that only cares about the beginning and the end. It doesn't care at all about the journey you took to get there. Here's the absolute best way to think about this. Imagine you're climbing Mount Kilimanjaro. The total distance you hike will be completely different depending on which trail you take, right? A long winding path is much farther than a steep, direct one. The distance you walk is path-dependent. But your change in elevation from the bottom to the top, it's always 5,895 meters. It doesn't matter which trail you took. Your altitude change is path-independent. It's a state function.
And just like your elevation on that mountain, enthalpy is a state function.
The total change in energy between your starting chemicals and your final products is always the same. It makes no difference if the reaction happens in one single step or if it takes 10 weird intermediate steps. Only the start and finish matter. So this leads us directly to Hess's law, which is really just putting that idea into words. It says that if you can figure out a way to represent your target reaction as a series of other, smaller steps, you can just add up the enthalpy changes of those little steps to find the total enthalpy change. It's like chemical Legos. You just add the pieces together.
All right, enough theory. Let's put this incredible tool to work and finally solve our puzzle. Let's say our goal is to find the enthalpy change for turning solid carbon into carbon dioxide. Even if we can't measure that reaction for some reason, Hess's law gives us that clever indirect path to the answer.
So instead of trying that direct path, we're going to use two other reactions that are easy to measure. First, we'll take the reaction of carbon to form carbon monoxide. We know the energy for that one. And second, we'll take the reaction of that carbon monoxide to form our final product, carbon dioxide. We know that one too.
Now watch how this all fits together. When we add these two reactions up, you'll see that the carbon monoxide that's made in step 1 is immediately used up in step 2, so it just cancels right out. And what are we left with? Our original target reaction. So because of Hess's law, all we have to do is add the enthalpy numbers, -111 plus -283, which gives us our final answer, -394 kilojoules.
And just like that, puzzle solved! How cool is that? We used our knowledge of state functions to take a clever detour and find the exact energy change for a reaction without ever having to actually run that specific reaction in the lab.
And this isn't just some neat classroom trick. This is a fundamental tool that scientists use every single day. It lets them figure out the energy involved in all sorts of processes that would be impossible to measure directly, from designing new industrial processes to understanding the complex chemistry happening inside our own bodies. So enthalpy is literally the language of energy change that's happening all around us, all the time. It's what determines the power in a gallon of fuel and the energy you get from a slice of pizza. It is an absolutely essential key for unlocking the energy puzzles of our world.